So the next segment is on the DART satellite, which was the double asteroid redirection test. It seems pretty cool. It's the first dedicated planetary defense mission we've ever sent, which is awesome. And yeah, so it's going to a dual asteroid pair. If you've seen Scott's video, then you know this. It's going to a dual asteroid pair where there's a smaller asteroid orbiting a larger asteroid. Basically, they're just doing this to see what sort of change we can make to the orbit of an asteroid. And you know, so this is a small asteroid. Let's not kid ourselves. It's a small asteroid in a in orbit around another, you know, small asteroid, medium-sized asteroid, probably. So it's not, you know, we're not like turning away the Armageddon asteroid right now, you know. That's not what this is about. This is more about quantifying the effects of a collision of a satellite of a certain known mass with an asteroid. And you know, the way that even if, you know, we were trying to stop an Armageddon asteroid, you know, it wouldn't be like blowing the thing up or something. It would be a minor change to its trajectory where, you know, okay, in, you know, 4 more passes of the Earth in 50 years, when it's projected to hit us, it will actually instead miss us by a certain amount. So that sort of is the goal with this mission, is to quantify the effects of doing something like this. So it is a, how would you say, forceful impact. Basically, we're just running the satellite into the asteroid, and we're going to determine what happens to it. So I think this asteroid was chosen because it's it's close enough to Earth that we can see it. Because the smaller asteroid is orbiting the larger asteroid, we can look at the larger asteroid, we can see the smaller asteroid pass in front of it, and then we can quantify any changes to its orbit. There's also a nanosatellite attached to the double asteroid redirection test satellite, which will pop out and hopefully be able to get some better data on how exactly the mission went. DART was launched November 24th. I didn't realize it was that long ago. Pretty cool though. I saw the launch from my house. So it launched out of Vandenberg. It launched south. I'm sort of like an hour south of Vandenberg. So yeah, it was cool. I popped my head out to watch it. It was sort of foggy out, so I didn't get much. I got like, you know, my wife actually saw it before I did, but it was like, you know, maybe a minute into flight I saw it, and then maybe by 3 minutes into flight we couldn't see it anymore because just the cloud layer had obscured it, but had obscured the Falcon 9, that is. But still pretty cool. And, you know, I was looking for the Falcon 9 coming back down, but didn't catch that either. So, although I think that happened pretty far south. Anyway, so yeah, DART is a project between NASA and Johns Hopkins Applied Physics University, Johns Hopkins University Applied Physics Laboratory, JHU-APL. When you talk about, you know, I mean, you think of like the goal of SpaceX, you know, make life multiplanetary. Why is that? Well, because we want to make sure we have a backup plan in case life, you know, becomes extinct on Earth. Asteroid is a serious possibility for you know, causing a mass extinction event. So this is a great thing to do. This is a great thing for NASA to be doing, and I think, you know, this sort of mission has a lot of public support. You know, part of it is because they don't really understand the problem, right? They just see Armageddon and they think that, you know, we're going to get hit by an asteroid, and that's what NASA should do, is planetary defense. Which, you know, I mean, eventually we'll get hit by an asteroid, but probably, you know, statistics are with us, right? At least for a while. But you never know. So, pretty cool mission. I'm excited. It was cool because it's the first interplanetary mission of the Falcon 9. And I did not watch the entire launch, actually. I don't know why I didn't, because I was thinking about it beforehand. I was like, oh, I want to like watch it to like see when it burns and how long it burns and everything. I didn't watch the second stage at all. I just watched the first stage. I looked for it to come down, and then I left. I don't know what the heck I was doing, but anyway, I do want to watch that just to see the Falcon 9 perform an interplanetary burn, since it hasn't before. So that's pretty cool. Collision is slated for 26 September to 2 October 2022, so pretty soon, less than a year from now, which is pretty cool. And yeah, they'll have some good data on it, I'm guessing, in the months to follow that. So super exciting, and hopefully, we can get more funding for bigger and even cooler versions of this. There are actually a couple other things about DART which are pretty cool. So I guess one of the things about DART is it's orbiting it's going to impact an asteroid that's orbiting another asteroid, right? I think the two asteroids are called Didymos and Dimorphos. I don't know which is which. I think Didymos is the larger one. Yeah, it's the larger body. So Didymos is 780 meters across, almost a kilometer. Dimorphos, the moonlet, is about 160 meters in size. So NASA on their DART page talks about 140 meter class asteroids, and apparently those are the ones that have a significant chance of impact to life on Earth in the case of a collision. However, of course, larger asteroids we can see quite easily, right? So like Didymos, for instance, at 780 meters, is not in the class of asteroid NASA is really interested in seeing or in redirecting, because we expect we've identified all those asteroids and that we know none of them pose a risk to us. And if any do begin to pose a risk, we'll know well in advance. However, the smaller asteroids, like in the 140 meter class, NASA expects that we've only identified about 40% of those, and those are still enough to cause an extinction event on Earth, and be a real threat. So that's why NASA is targeting this size of asteroid, and I just thought that was super interesting. And yeah, so the mission, like I said, it's actually only altering the orbit by about less than 1%. But, it's a minor change. It's just a test. This is a small satellite. It will be hitting quickly, a kinetic impactor. But this is a good test to see what sort of effect we can have on the orbit of an asteroid. So the other thing that was cool about this was that it has solar electric propulsion. Specifically, it uses the NASA Evolutionary Xenon Thruster commercial Next C solar electric propulsion system. So what this is an ion thruster. It's called solar electric propulsion because it uses the solar power generated by the solar arrays to power the ion thrusters. So it's a little, I don't know, it's not like a solar sail or anything, slightly counterintuitive in my opinion in that regard. But that is pretty unique because it's not using onboard fuel, right? So that's important. So it is solar electric in that regard. So it is using onboard fuel technically, but it's just using ions, charged ions. In this case, xenon. So these ion thrusters have been around for a long time. Xenon is the most popular choice because it obviously it's a noble gas, so it doesn't react with anything, and then also it's basically exhibited the best characteristics of any of the gases studied thus far. If you're familiar enough with the Starlink system, the Starlink satellites in particular, you probably know that SpaceX also opted for an ion propulsion for their Starlink satellites, and they went with a krypton thruster rather than a xenon thruster. So I did some research on this with an old NASA paper from 1992, and then there's a couple other papers as well that talk about specifically the difference between xenon and krypton. But so krypton, as you would expect, because it's a lighter molecule, it does have a higher specific impulse, both theoretically and experimentally, because theory doesn't always translate to experiment, right? Because there could be technical issues with how the krypton goes through the thruster and reacts to the cathodes and everything. But experimentally, it does have a higher ISP, as you would expect. Also, obviously, because it has a lower mass particle, it's also going to have a lower thrust. So pluses and minuses there. Of krypton vice xenon. The thing about krypton that is interesting is it has some more maintenance issues than xenon. Specifically, let me see if I can find the introduces potentially life-limiting issues associated with internal erosion of cathode potential surfaces in the discharge chamber due to ion sputtering. Now, I am not yet an expert on ion propulsion, so I'm not going to act like I know what that means, but it's just worth noting that krypton does have some issues that you wouldn't see with xenon, specifically as relates to the longevity of the thruster. So that's something to keep in mind for these. Now, has SpaceX fixed that? Maybe. I think more likely, their satellites are only designed to, they're in low orbits. They have limited, supply of krypton, right? So they're only expected to be in orbit for about 5 years and then deorbit. So I expect more than likely they said, these things are relatively cheap anyway. If we lose one or two due to maintenance issues, no big deal. And by the way, it's not going to be up there that long. Although, another trade-off you have to think about with the krypton versus xenon thruster is because the krypton is going to be lower thrust, it's also going to need to fire more. So these things. So for instance, the next C thruster had a specific impulse of one. So this is the one on the DART vehicle or satellite. Had a specific impulse of 4,190, which is state of the art, especially for a satellite. I think even the experimental results in the 1992 paper, which this is like in a lab, saw. Even at 0.7 efficiency, almost 0.8 efficiency, less than 3,500 ISP. So the fact that NASA is able to squeeze 4,200 ISP out of this xenon thruster is quite impressive. Because the krypton thrusters are lower thrust, they'll have to fire longer. And these things are not putting out a lot of thrust. It's measured in micronewtons. For instance, the next is it says less than 13.5 micronewtons of thrust. So these things are firing for a long time, and on the order of days, right? And so SpaceX is going to have to fire them more. Not only are they life limited, they're also being fired more, which is more of an issue for the life limiting problem. So I don't know. Interesting. We will see what way industry goes with it eventually. Like I said, I'm not an expert on ion thrusters. I am very interested in the topic, so I want to do some more research on it and get more information. But I don't know enough right now to talk too much about it. But anyway, thought that was cool and worth mentioning about the DART mission. But yeah, that's pretty much it. Cool mission. First asteroid, sort of planetary defense mission ever. So that's tight.